Cuban. I teach in the engineering department, primarily electrical engineering and computer engineering courses. To give you a little background on this next project, one of the issues we faced historically over the years with electrical engineering students is the creation of printed circuit boards, which is kind of hard to do and usually not very successful with the kind of like hobbyist methods that we've tried. So a few years ago, we had the good fortune of getting a grant that allowed us to purchase a lot of equipment to create professional circuit boards. And so we had the equipment, we had the room, and unfortunately the one thing we didn't have was time to learn how to use all that machinery, about 4 or 5 different machines. So we did have the good fortune of having a couple of really good students that took that upon themselves as their project for a semester, and they did a really good job. So with that, I'd like to introduce Alan Whitehouse and Josh Peaugh.
I'm Alan Whitehouse.
And I'm Joshua Peaugh.
We developed a microprocessor circuit board that we call the Tomato. We would like to thank everyone who assisted us with the project. Don Moore, Dr. Cuban, Dr. Mitchell, Mr. Frazier, and Mr. Nelson. I'm sure we'll leave you out, but we definitely received a lot of assistance from all of you guys. As part of the applied engineering building expansion, USI has equipped an electronics circuit manufacturing lab. The lab facilitates the construction of surface-mounted circuit assemblies, like Dr. Cuban mentioned. Joshua's going to be passing around some examples of these surface-mounted components. They're small in package size, and they're optimized to be placed mechanically on the circuit boards. Very difficult to handle by hand and build circuits with, but they're very inexpensive. This is the first opportunity for most of the equipment in the lab to be operated. Our goal is to initialize the fabrication equipment in the lab, and to this end, we designed and created a microprocessor development board. The primary design criteria for our board was low cost per board and compatibility with Arduino shields. The construction of a circuit board using the equipment located in the Circuit Manufacturing Design Center can be broken down into 3 major divisions: design, mill, and assembly. In the design stage, we create the circuit schematic, we lay out the traces and the components. Then we go in the mill, we actually physically drill and electroplate through holes and cut the isolation traces. And then we assemble the board. We take the completed board and we start putting the components onto the board, and then we solder the components on. Circuit design. Arduino is an inexpensive microprocessor board with readily available circuits which can be added to the base of the board. These additional circuits are called shields, and they reside right across these headers right here, and they will sit across the top of the board. They're inexpensive, they're readily available, they're commonly available. So the Arduino has 20 general I/O pins, uses 5 and 3.3 volts, and it has this unique header setup. In addition to that, the microprocessor used by the Arduino is very basic, without a lot of options found in a more robust microprocessor. We wanted a microprocessor to be able to utilize some additional communication protocols not available in the Arduino boards to interface with additional hardware. So we wanted to be sure we had I2C, CAN, SPI, and RS-232. Additionally, we wanted to be able to program our board without using additional hardware. We wanted to be able to just plug it into the computer to drop the firmware in and to be able to make the board operate. We didn't want to create the need for additional gear to make the thing work. The design of the circuit was broken up into modules, primarily function diagram type stuff. So I broke it up into the microprocessor, power, RS-232, CAN, USBDM. USBDM is an open source project that handled that programming side I spoke about earlier. It allowed the computer to interface directly to the microprocessor. Data sheets were chosen for each of the major chips in each module. Data sheets have great information on them that can give us sample circuits to make each one of the major modules The only exception to the rule is the USBDM. It's an open source project, and we had never used it before, so created a mock-up of it, and we actually burned a standalone board for the USBDM just to verify it would work before we built our circuit around it. So that was the only exception. They were created using a software package we have here at USI, National Instruments Multisim. And here's an example of the circuit. It's the schematic. Not very blurry, unfortunately. As you can see, it's broken up into modules. Each major module, you have the inputs and outputs, and they all interface with each other. Next step in the design was the physical layout of it. So that circuit, the multi-sim outputted to another software package that allowed me to lay out the traces and the through holes and to create all the physical requirements for the board, size of the components, how wide all the spacing is, and to run all the wires in between. This software package we used there was also a National Instruments package. It's sort of the sister or the companion software package, and it was called Ultiboard. And it actually was capable of producing what's called a Gerber file. It's just a specific file format that we use in the micro-manufacturing world for the milling machine. And it also is capable of outputting this really nifty-looking 3D representation of what my circuit board was going to look like, which is actually very handy because you're dealing with really small components, and layout sometimes becomes very crucial, making sure they're not going to bump onto each other, make sure you have enough clearance above them and around them. So this was the end result of that software package. Next, we took that design and we loaded it into our milling machine. The milling machine imported the Gerber files and took the files and converted them into a format that it could run the milling machine. The primary purpose of the milling machine is what's called isolation milling. The output of the other files basically has 3D data that tells it where each trace is. If I just sent that data to the milling machine, it would cut the trace. We actually want the negative of that particular data. So the milling machine is capable of looking at that data and creating a mirror image of it to run the components off of. Okay, so the first step in it is we drill all the through holes. Some of the circuit traces, because this is double-sided copper board, it's a copper sheet affixed to a thin piece of fiberglass on the top and the bottom. You run into some cases in which you want the electrical conductivity from the front to the back. The way you achieve that, you drill a hole, you coat all of the holes that need to be electrically conductive. You coat them with a conductive ink, and you end up coating just the edges of the hole. Then you electroplate it, and you end up putting a thin layer of copper on the top and the bottom, but more importantly on the inside of that hole. And that gives you the electrical conductivity from the front and back, wherever you have through holes that need to connect them. After you've done the electroplating, you go back to the milling machine, and it uses these really small 1/4-inch milling bits, and it mills those traces. We currently have sizes down from about 32 mils to 8 mils. Mils is sort of an old standby for this precision machinery. A mil is 1,000th of an inch, so 32 thousandths of an inch to 8 thousandths of an inch. These bits have a limited service life. We were getting about 10 feet of runtime on these things before they die. So we try to minimize the amount of use that the smaller, the more expensive bits had, and try to maximize the amount of use used by the larger bits, which were the least expensive bits. Here's one of our finished boards, front and back. And it's actually this board right here. Right here you can see a close-up on some of the smaller traces. And right there, right here, you can see a pencil lead up in there. That is I hit the button, sorry. That is a 0.5 mechanical pencil. That's the smallest commonly available engineering pencil, just so you can get sort of an understanding of how close these traces end up being.
Once the trace has been fully milled, it's time to place the components on the board. For this, we used a pick-and-place machine that USI purchased from Mancor. It is a machine that's designed to rapidly place the components and solder paste on the board. a varying amount of components. It has information already on the most common components: resistors, capacitors, inductors, and a lot of the more common integrated circuits like some microprocessors. And for the information it doesn't have, that information can be easily programmed in. It uses a visual programming method to determine placement locations with the two cameras, one of which you can see here attached to the placement head. And with that, it also takes images of each component to verify that it's picking up the correct component and has it oriented properly. To load the components on the machine, we used two different methods. The first one was using feeder reels. These are used for larger reels of components. Alan's passing around some examples of the feeder tape. It's a lot like a film reel. These reels are used for components that are either very cheap and small, or just very easy to place using such methods. The most common would be resistors. As you can see from the tape that Alan just passed around, I think that one's for a resistor. It's very small. Those components were very cheap as well. We were able to purchase those for less than a penny per unit. The reels were primarily used for components that we could purchase in quantities of up to about 1,000. Currently, with the hardware we have, the machine can hold up to 32 different reels of components. With some additional hardware and a couple modifications to the machine itself, it can hold up to 128 different reels of components. The second method we used was what's referred to as free placement. Free placement is, as you can see here, just placing the components in a line inside the vision range of the cameras. The only limit to the number of components can hold by this method is determined by how much space is left inside the machine. Through this method, we were able to place components that were unusually sized or unable to fit on reels, such as the microprocessor here or the clock crystals here. And typically we use this method also for components that we could not order a lot of due to a higher cost, again, such as the microprocessor. Now for this method to work, the components had to be in very straight rows, all oriented in the same direction, and evenly spaced. The first step in actually running the machine was dispensing the solder paste. Without solder paste, the components would not be attached at all. The component libraries have records for exactly where and how much solder paste needs to be dispensed for each component. And we have a short video clip here of the machine actually dispensing the paste.
Right here you can see the syringe that holds the paste. We load it up with the solder paste, and we actually size the nozzle based on the viscosity of the paste.
Now the library records were not perfect, but they were excellent starting places. And again, the machine uses a camera to determine exactly where to dispense solder paste. According to the manufacturer, the machine is capable of handling 6/1000ths of an inch of diameter of dot size, or 6 mils. Due to the viscosity of the solder paste we were using, we were unable to get that small. We got about 15 to 20 mils. Solder paste is a combination of metal balls of solder and flux. If the flux is too viscous or the solder balls too big, they won't physically fit through the needle. That's the problem we encounter, but that can easily be remedied by a different type of solder paste. Once the solder paste was placed, we moved on to actually placing the components on the board. The machine is capable of very high-speed component placement at 5,000 components per It can be placed at your standard 90 or 180 degrees, or it can be angled at 35, 55, 60 degrees, or any type of circuit that's designed. It uses the cameras to visually verify the correct location and type of component that it's placing. And here we have a video of it actually placing components. It's moving at half speed through this video, so the work can be seen with decent clarity. As you can see in the front, it's taking components from feeder reels, in the back from free placement. And it switches the nozzle size depending on the component that it's picking up and placing. It can also vary speed mid-run to pick up and handle different components. Once all the components were placed on the front and the back, the components had to be soldered to finish off the assembly. To handle this, we used what's referred to as a reflow oven. The reflow oven is a programmable oven that heats and solders the entire board simultaneously, front and back. The software setup took about 10 minutes, and we programmed it using a heating curve that we obtained from the manufacturer of the solder paste. This shows what temperatures the solder paste needs to achieve in order to be melted completely. And we have a video of what the reflow oven is capable of. This is not our board, but as you can see, even the components that were aligned improperly are moving into place as the solder melts. And here is an image front and back of the complete board. This guy here. Some financial considerations. First things that we have to take into account were what are referred to as non-recurring engineering costs. These are our research and development and prototyping costs. We broke labor up into two components, circuit design and machine debugging. Each cost assumed at a student labor cost of $15 per hour. Design and machine debugging all total took about 260 hours, which you can see the costs here. And then there are prototyping materials. These are the components that we ordered, including in the large quantities, such as thousands of components, total to 410. And then there were expendables that we went through, such as the conductive ink for electroplating, tape, markers, other basic expendable disposable tools that we needed, and bits. And you can see the total on screen.
Well, the overall goal was to make a small board that was usable by students that they could crank out and learn how this equipment operates. So we wanted to create something that the students could use to learn how to utilize the lab. In order to recreate these, it's going to take them about 7 hours. 6 hours of that is going to be physically milling the circuit board. The milling machine is the largest labor investment involved in creation of this thing. Then about an additional hour to place the components and to solder them on. We have about $20.30 worth of components on this board. So it's relatively inexpensive. Project outcomes. The circuit lab is operational. We overcame several technical issues. The equipment works. We have a better understanding of some of the design limitations for the equipment. We were given just this raw equipment and we didn't know how small we could make the traces, what size holes would be most optimal, how fast to place the components, and what shape and sizes the machinery was capable of, what shape and size components the machinery was capable of operating. We have a library we have built with a lot of that now understood and fleshed out. And there were several technical issues that we resolved, as you're going to find with any new startup here. Any questions?
All right, questions? So Alan and Josh, can you talk to us a little bit more about the lessons learned from your senior design project? And how much time did you spend up in the AEC?
We spent a considerable time up in there. A lot of time, there was a lot of design time involved as well, right? Interfacing with the software. And fortunately, we had some home versions of that, so we were able to do a lot of that at home. The AEC, it took us a considerable amount of time to get these milling machines operational. We had several technical issues. I had a couple of sessions where I was talking live with tech support, trying to get these things operational. I really didn't keep a logbook of the hours, and that's one of the things I would change if I was doing this in the future, is keep a better assessment of how much time we spend on it. What we learned that we would do differently. There are some design parameters that we weren't aware of. When you can have a circuit board, you can send these guys out, you can send your design out to a fabrication house, and they will mass produce your board for you. I went by those parameters, what size traces they were capable of operating, what size hole sizes they were capable of milling, and I added about 50% onto that size, thinking our mill would be capable of handling that. We didn't add enough. We should have left a whole lot more space in between our traces. So in the future, we would change some of those design parameters. Josh, any big things that you came away with?
Really, the biggest thing I came away with was, I suppose, a better understanding of how to handle problems such as this and learn new equipment that no one else around us knows how to use fully. And those kinds of skills aren't valuable anywhere, really.
Alan, thank you for the presentation, Joshua. What labs can be designed for the students to learn how to design and build circuit?
Yeah, we've actually been talking about this a little on the side. I really think it'd be very practical to design a simple circuit from concept to execution. And I think if we went with a simpler board, I think it'd be very feasible to have the students create something, mill it, then place all the components, and then have a functional device at the end. So
It would have to be a very simple board, though. As we mentioned, this microprocessor board took 7 hours of fabrication time. I don't think anyone wants to have to babysit a milling machine for 7 hours for a lab. However, the USB ham, it took what?
that was 45 minutes of mill time.
A board this small, front and back, total was 45 minutes mill time. So having a simpler board, such as just a power source, push a button, light a few LEDs, that would be a pretty simple one. Could even be done in less time.
Very good work, guys. We're really going to miss you seeing you over there the weekend and nights. It's just not going to be the same without you over there. You answered just answered one of my questions. I was curious about the production time. If you wanted to make multiple boards, I mean, the milling process something you can just let it go lights out, or do you have to babysit it?
The milling process is the serious time log of this, okay? The mill, we almost have to divide the circuit lab up into two types of equipment. The milling machine is excellent at making prototypes, one, two ofs, right? To test your design, proof of concept. The placement machine, it is capable of 5,000 components per hour. This is an industrial machine for cranking out multiples of boards. So it takes almost the same amount of time to do one board as it would to do 20 boards with it. Okay, so the serious drawback in time, the serious time hog, is going to be the milling. Now, if we were going to create 100 boards of some design, we would create a prototype. We'd make 2 or 3, we'd prove its functionality. Then, if possible, we'd send out, we'd get that board produced somewhere. relatively inexpensive. And then you can run it through the placement machine, and it would be no issue at all to create large quantities of whatever project we were doing.
One more question. You said 10 feet of milling length for the smaller bits. How many boards does that translate into?
I'm sorry, how many what?
How many boards would that translate into that you would guess?
That's about 3/4 of one of these boards.
3/4.
Front and back.
That's, you know, the big board, that's 3/4 of the way.
Great project, guys. You mentioned that the milling machine is obviously the time hog from a production standpoint. What about the layout design versus the milling machine? I mean, if you had some students or somebody wanting to build, say, a simple amplifier circuit or something along those lines, how much time was spent on just coming up with the layout and all of that versus?
The hardest part of it typically is optimizing it for size, making everything fit in as tight of a component, in as tight of a space as possible. If size isn't a huge issue, like with this board, you know, I wasn't too concerned. I wanted it to be about this size, right? So this board didn't take me that long to design, maybe 2-3 hours. I could probably sit down and do this board now in about 20 minutes. There are libraries for these components, like Josh mentioned with the pick and place machine. Multisim and Multiboard have libraries for most of these standard components. And with some practice, you can create your own components relatively quickly. But almost all the components are already in there, and it's a matter of connecting those traces up. And that can be done for the simpler projects relatively simply. It's not that difficult. The more difficult projects where you have multiple I/O pins, you have large packages with pins going everywhere, that takes some time.
One more. On the milling machine with your different cutters, do they offer a variety of cutters for different types of cutting? I know in the metalworking side, you have roughing cutters, you have high speed, high movement. Do we have room to vary our tooling to increase the tool life?
Yeah, it automatically picks up and play, and I didn't mention that, but yeah, it holds 32 implements. They make a variety of different implements. This is it's a standard 1/4-inch mill bit, so that, yeah, they make, the mill bit we're using now is optimized for cutting copper. They make some that are optimized for cutting plastics. They make them in a variety of sizes. They make a router bit, they make drill bits, and we have some of that, but that might be something we need to look at. Maybe there's a better bit that would be better optimized for the type of copper we're using.
And does that have a variable RPM?
It does have a variable RPM, and that was part of the setup, was getting that RPM set up right. We were given a generic chart from the manufacturer, and again, we're not sure if that's optimized or not. So that would be someplace good to look at, that we might be able to improve performance.
All right, folks, let's give them a hand.